Trying again, we welcome Greta Panova from USC. We'll talk about Ehrhart positivity and plane partitions. Please go ahead.
Thank you very much. Thank you very much for the invitation and the opportunity to speak to a different crowd than I usually see. So full disclosure, last week I asked Graham, what do you want to hear about? And he ordered the result about ordered polynomials. So this is, I wrote the talk yesterday. If there are any typos, please excuse it. So I'm gonna start with a Putnam problem. And so the story, of course, behind this problem is actually I was on the Putnam committee for the last 3 years, so I was responsible for the content of the Putnam competition. And so I found the results in a paper of Luis Ferroni that was very beautiful somehow, and made a very nice Putnam problem. So it made it on the competition, and the results as the following. So suppose you have two positive integers k and m, and we are going to count the number of sequences of integers that are weakly increasing, sequence x1 up to xk and y1 up to ym, and the number z satisfying that the x's are bounded by z, which is less than or equal to n, and the y's are bounded by z, which is less than or equal to n. And the question was to show that f of n can be expressed as a polynomial in n with non-negative integer coefficients. So if the z was not there, we have two disjoint sets of multi-sets. It's going to be given by the product of two binomial coefficients, and then it's easy to see that this polynomial is non-negative. So the z is making things a little bit weird. So in particular, if you actually want to enumerate this, and I'm actually going to show you a solution from an anonymous Putnam participant, which was better than anything we actually had. So this fkm, then you can just enumerate by listing the possible values that z can have, and for each one of them, the x's and the y's are these two binomial coefficients. Okay, so you have this sum. It's not at all obvious that this is a polynomial, but I think you guys should. For all of us, it's clear that's no, so I'm not going to prove this part, so that it is a polynomial. But let's see how we can figure out the positivity in this case. Well, one observation is that if you subtract two consecutive values of this function, you get just the product of two binomial coefficients. Sorry. And these binomial coefficients, if you write them as polynomials in x, well, they become zero if x is 0, -1, and so on. So this should be minus m minus plus 1. And f of 0 itself is gonna be 0. So by induction, you're gonna get that the value of this function is 0 for all this guy. So in particular, this is divisible as a polynomial by x plus 1, and so on up to x plus m. So there is some other polynomial here in x. And now we can use this knowledge again, use this same difference identity here to figure out that to cancel out some of these factors, and we get another polynomial which also has a lot of zeros. In particular, we get this relationship between the values of the qx and qx minus 1. And what you notice here is that when j goes from j to j plus 1, you get a negative factor. So if at some point this value is positive, the next one will have to be negative, and so on. So we have a polynomial which is oscillating between positive and negative. Intermediate value theorem tells you it's got to cross the x-axis every time it goes between these two values. So for every interval of j, there is going to exist some rj such that qrj is equal to 0, and then you can just factor your fkmx completely into those factors. The r's are negative, so basically this polynomial has all negative zeros, and if you decompose it, of course, it's going to have a positive coefficient.
I guess you knew its degree up front, probably.
Yeah, so you know the degree. Yeah, so there are a few details that I'm skipping here, but yeah, so you know what kind of polynomial it is. You know the degree, and that tells you the rest. So that's not how we solve the problem. We used a lot of various binomial identities, transformations, and so on. So that was a very nice solution. Unfortunately, that solution does not generalize. So I'm just including it here, just for you guys to admire it. But what does generalize in the whole business of this problem? So let me start with with the object of our study. I come from algebraic and numerative combinatorics, and we like to study partially ordered sets. So here is a partially ordered set. You have some elements, you have some partial orders between them that should be, of course, consistent. So you can present this Hasse diagram as an acyclic directed graph. And the first thing you want to count, so in the numerative combinatorics, is the number of linear extensions, or the number of ways to totally order those elements. So here we present this by putting the numbers from 1 up to n in places of these elements so that they respect order. In this case, there are exactly 5 possible linear extensions. And the number of linear extensions of a poset is E of p. Here are some examples that hopefully all of you know. So this is the chain, is kind of trivial, that everything is ordered. The anti-chain is just all possible permutations, anti-chain an. So if you have 2 disjoint chains, you just have to pick the elements in one of them. So you have binomial coefficients. If you have this ladder type poset, you have Catalan numbers. If you have the zigzag, you get Euler numbers. So you get, and actually it is a theorem that you can get every number realized as a number of linear extensions. And as you might expect, in general, this problem is computationally hard. So you cannot expect to have a nice formula for every poset, and it is computationally hard in a very formal, strict way. So this shan't be complete, even if the poset is of height 2, meaning that the longest chain has 2 elements. Okay, so there are no explicit formulas there. So what can we do if we don't have formulas? This is just for the linear extension. So now let's generalize. So what do we do with mathematics? We just generalize stuff. And okay, so I wanted to say that these types of the linear extensions of posets are themselves subject to some very interesting problems, and one is the one-third, two-third conjecture, which in some sense motivates us to study various poset inequalities, log concavities, and so on. There is a cross-product conjecture and so on. So I'm not going to talk about this now, but it is a topic that all the things that I'm going to talk about are somehow related. Okay, so the notion of linear extension can be generalized. So this time we are mapping the elements of the posets to the elements of the interval from 1 up to t. T has to be an integer here. and they should satisfy, they should respect the partial order in our poset. And we, of course, would like to count these constructions as well. So it's, yeah, so it is hard to draw them all, even for this small poset. There are too many, even if t is small. But let me show you how you count. In general, you take the poset. So what you need to do is compute the order, to compute the order ideal, the lattice of order ideals. In practice, what this looks like is you choose a number k that is less than or equal to the number of elements of the poset, and you choose a linear extension. So, well, actually not a linear extension. So you choose an order preserving map that has the numbers from 1 up to k appearing. And then all you need to do is reassign these numbers from 1 up to k to some elements of this interval. So, for example, if you have all numbers are different, let's say you take this example here with the first linear extension, that gives you an order ideal chain in the order ideal lattice. So first you should put this element, then you add this other element too, then the element that's labeled by 3, and so on. Here is another one, and then all you need to do is choose which elements from the interval are assigned to this 1 up to 4. In this case, these are t choose 4 elements, and there are 5 different ways to order them. So you get a term 5 times t choose 4. Then if you just have 3 distinct values, you get a lot more. So you get actually 10 possibilities. So here are some examples of how they work. And you add, and then you have 2 possibilities, which give, so if you have 2 distinct elements, then you have 6 possibilities, and so on. So the order polynomial then is just the sum of all these binomial coefficients times the number of chains of that size. So now you see it is a polynomial. So this is basically how you prove that this is a polynomial. And in this particular case, it's a polynomial with positive coefficients, but each of the binomial coefficients themselves does not have positive coefficients. So it's somehow an artifact of how you add things up. Another thing to notice is the leading term. So first of all, the degree is the number of elements, which in this case is 4, the degree of the polynomial. And the first term of this poset is 5 over 24. 24 is just n factorial. So 4 factorial, 5 is the number of linear extensions. So from this example, it should be clear that you always get the leading term to be the number of linear extensions over n factorial. And yeah, so that's basically the first observation you have for the order polynomial. It starts with number of linear extension over n factorial t to the n. The next coefficient is actually also has combinatorial meaning and is positive. And then from then on, you don't know what's going on. And so here are some examples of order polynomials. So when you have the chain, already you get this binomial coefficient. This has positive terms. If you have the anti-chain, you just get t to the n. So here you have the disjoint union of 2 chains. You have product of binomial coefficients. The Catalan poset that I showed earlier this is the order polynomial. This one is funny here. So if you have an anti-chain of size n minus 1 and you add one element that is bigger than all of them, this is what this poset is. Well, you have n-1 factorial ways to order them. And the number of order preserving maps is this guy here. So this is the way it's written. It's not a polynomial in T, but it is what's called the Faulhaber function. And it is actually a polynomial in T for every n, polynomial of degree n. And if you have, so I will define this in a moment, if you have the partition lambda, let's say this is a by B rectangle, so you're filling the numbers. So the poset is an A by B rectangle, and the order of the cells is the natural order, which comes from the relative positions of the boxes. So the number of linear extensions is given by the hook-length formula, and the order polynomial is given by the hook content formula in this case, or McMahon's identity, which you can write like this. And in this particular case, you get a polynomial with all linear factors with positive coefficients. So the whole polynomial has positive coefficients. And so here is already an example for the second. So these guys. So the anti-chain plus an element. This is, we call it the mother of all counterexamples. So if you want to check if something is true, that's the poset, the poset to look at. So this as a poset, this is what it looks like. So you have 4 elements that are all smaller than the 5th element. And if you compute the order polynomial, you get this guy. And as you can see, the last term is negative. Has a negative coefficient. So we can't really hope that these order polynomials will always have non-negative coefficients. Already we have this counterexample here. But we may hope to sort of classify which families of posets have positive coefficients.
I think then I don't understand your notation for the order polynomial in the second last row, the anti-chain plus 1 element.
This
Yeah.
So this is a function, right? But it turns out it is a polynomial in T.
It looks like a polynomial in T.
No, so the way it is written here, it's the sum of the integers so 1 to the n-1, 2 to the n-1, and so on up to t to the n-1, which only works when t is, of course, an integer.
Aha.
But if you sum it up, it turns out it is a polynomial. This is Faulhaber formula, and if you sum the integers from 1 up to t, it's t plus 1 choose 2, right? And if
of course, yeah.
the squares, like 1 squared, 2 squared, and so on up to t squared, so then you get t times t plus 1 times 2t plus 1 over 6, and so on. So there is so for every n, if you do this, you're gonna get a polynomial of degree n. And this is the Faulhaber for n equals to 5 function. So you can check in Wikipedia that when you write it as a polynomial, it gives you this.
I was confused about n versus t. Thanks.
Yeah, so n is the number of elements in the poset, so it stays fixed, and t is basically how large the elements in the linear extension can get. Okay. Okay, so yeah, so from what I was saying earlier, we should believe that this is always a polynomial of degree n, which is the number of elements in the poset. And so for this particular case, we get a negative. negative term. Okay, so coming from algebraic combinatorics, there is a very natural class of posets that we study. They have to do with the representation theory of the symmetric group and statistical mechanics, Dimer model. So there are all these other objects that they are associated with, but let's just look at them as partially ordered sets. So if you have taken integer partition, for example, here lambda is 5, 3, 2, you can make the Young diagram of that partition, which consists of lambda 1 boxes on the first row, lambda 2 boxes on the second row, and so on. So in this case, 5, 3, and 2, and they are all left justified from here. Because the numbers of boxes are weakly increasing, you're gonna get that this border here, I don't know if, can you see my mouse? Yeah, so this border here is actually a lattice path that goes up and to the right. And now you can generalize this Young diagram to a skew shape when you take one partition / another one. What this means is that you take the big partition and then you just remove the smaller partition from it and you consider the boxes that are between the two. So this is what's called the skew shape. And so where those skew shapes show up, so first of all, straight shapes index they index the irreducible representations of the symmetric group and the general linear group. The characters of those for the general linear group would be Schur functions, and you can also define a skew Schur function for such a shape. If you expand it into the regular straight shape Schur functions, you encode the constants are the Littlewood-Richardson coefficients, which give you multiplicities in tensor product of irreducible representation. So there is punchline is there is a lot of algebra encoded just with these shapes. Okay, so you take these boxes. Let's say that we take this example, and we make a partially ordered set out of them. Basically, box. So the order of the boxes are the elements in this partially ordered set, and the way to imagine is that the entries are increasing as you go from left to right, and they're increasing as you go from top to bottom along the columns. So here is our partially ordered set that corresponds to this Young diagram. So this corner here where my mouse is, for example, the element D in the partial order. This here is going to be the element A, and so on. And then a plane partition, the definition of a plane partition, which I'm gonna do reverse plane partitions for what we're gonna do, it doesn't really matter, is an assignment of the numbers 1, 2, 3, whatever to these boxes so that they are weakly increasing along rows and weakly increasing down columns. So we are allowed to have repetitions, but the condition is that every column has the integer weakly increasing and every row has the integers weakly increasing. And implicit here, for example, is that this is a plane partition with entries between 1 and 3. So I get to choose what we put here in terms as numbers. And now from this description here and the fact that this is really a partially ordered set, you get that these plane partitions are in fact order preserving maps, right? So this assignment of numbers is respecting the orders in the boxes. And so in particular for this example, the order polynomial then for this poset here, this associated to the skew shape, is the number of tuples, well, 8 dimension 8 vectors, A from, so going from A to H is the last element, which take values from 1 to T. And here are the inequalities that they need to respect that come from the diagram. So these are the rows. G is less than or equal to H is another row, and D is less than or equal to G. This is a column, another column, and so on. So this is what the partially ordered set looks like. And in particular, if we do plane partitions with elements from 1 up to T, and if we want to count them, this is exactly the order polynomial of this poset. So these are the plane partitions and the order polynomials of posets, but these are directly related to Ehrhart polynomials. So what's an Ehrhart polynomial? So take a polytope. So in our for what we do, our polytopes will have all there will be rational vertices. So you can define your polytope whichever way you want. You can either be some solution to a bunch of linear inequalities or a convex hull of points in Q to the n. The only restriction is that it needs to be bounded. So again, so we like to count stuff. So what's the thing we can count is the number of integer points of this polytope. So how many integer solutions are there to this linear inequality, for example, or how many integer points are there which are positive linear combinations of the vertices of the polytope. So whichever way you want to interpret this. And then again, so this is implicitly a theorem here that if you dilate your polytope by some factor t, if t is an integer, you can count the number of integer points. So here I have this my original polytope here, and I have dilated it by 3. We count the number of integer points in that dilation by 3. So if you do this for an arbitrary integer t and you count the number of integer points, it turns out if your vertices are integral, not just rational, then you get actually a polynomial in T, and this is what's called the Ehrhart polynomial. In this particular example, the polynomial is not so interesting. It's T plus 1 so squared. And if the vertices are rational, you just get a quasi-polynomial, meaning that there is some kind of periodicity to the polynomial function. So now we can put the two types of theories together. If you take the order polytope of a poset, so the order polytope is basically confined to the cube of dimension n1, so the cube of side 1 of dimension n, and the inequalities can be defined by the linear inequalities between the variables, so the variables xi is less than or equal to xj if and only if I is less than j in the poset. So for every partially ordered set, you can create this polytope, and it turns out that the Ehrhart polynomial of this poset, so the number of integer points when you dilate this poset by t, is the order polynomial evaluated at t plus 1. So why is this? Because, so why is there a shift in the variables? Because here you basically, when you dilate your poset by your order polytope by t, it's the same as choosing this vector from 0 to t. So now we have, instead of from 1 to t, we also include the 0. So we are actually choosing we have t plus 1 choices for the values of these variables, and these variables are, when you assign them values, they become an order preserving map for the poset. So that's why you have the order polynomial t plus 1. Okay, so the Ehrhart polynomial is a subject of study on its own in general, and the main question here is for which polytopes are the coefficients in the Ehrhart polynomial non-negative integers. So if we have an integer valued integral polytope with integer valued integer vertices, then the coefficients are going to be rational. When are they non-negative? So it's already false for order polytopes, even though you have this shift of t plus 1, as you notice, which makes the polynomial more positive in a way. There's still a counterexample. And again, this is anti-chain of 20 elements plus one element that is bigger than all of them. And this is the Faulhaber 21 function for 21 or 20. And this example was given by Richard Stanley in a math overflow post, and then later appeared in various papers. So the linear term here becomes negative. So remember, linear term is somehow important. The leading term in the Ehrhart polynomial is proportional to is actually the volume of the polytope. So that's another important quantity. So there is a way, if you have a matroid, I will mention this later, if you have a matroid, you can define a polytope associated to the basis of the matroid. Basically, the bases are going to index the vertices of the polytope. And it turns out those Ehrhart polynomials have also sometimes negative coefficients. This was a counterexample found by Luis in 2021. But despite the counterexample, Luis was still very somehow hopeful that the Ehrhart polynomial of the order polytopes of what's called the fence posets, which is exactly as the poset corresponding to a skew plane partitions when the shape of the skew plane partition is a ribbon, so it doesn't contain a 2 by 2 square. So those have non-negative coefficients. And here are some examples of these fence posets. So the Putnam problem that I started with, the poset is exactly corresponds to this hook shape. So you can imagine that this is a z here, and so you're putting the weakly decreasing numbers here and here. And the order polynomial, you can compute This has positive coefficients, so has positive coefficients already, the order polynomial. So if you do the Ehrhart polynomial, it's like substituting t plus 1, it becomes even more positive. Ribbon shape here, this is an example of a fence poset. So it's like a snake of boxes, or a lattice path described by these boxes. It also has positive coefficients. And so here is a thicker skew shape, and it turns out this one also has positive coefficients. So maybe it's not just fence posets, but that's what we set out to prove in the beginning. So what did we know coming into this? So this is what we're going to talk about now. What did we know when we started looking into this problem? So there is a lot in algebraic combinatorics that we can use. So if you have a straight shape, meaning that you just have one Young diagram and you're not removing anything from here. So the first thing that we study in algebraic combinatorics is the semi-standard Young law. So these look like plane partitions, except that now you have strict inequalities along the columns. So for those we can enumerate. So they come from sure functions. I mean, for us, it's not important what the sure function is, but it's basically a generating function, multivariate generating function for these shapes. And there's a lot of theory behind this. So if you want to enumerate the number of semi-standard Young tableau with entries between 1 and big N here, it is just an evaluation of a sure function it's called the principal specialization at 1, 1, 1 up to N. And this is given by the hook content formula. So this is this product. So the partition is fixed. The variable in this case is N. So this is clearly a polynomial in this N of degree little n, so the number of boxes. But I already see that if you take this shape to 1, plug in n many ones in here and evaluate the number, you get a negative coefficient. Okay, so these guys are not, so these are a little bit more restrictive than plane partitions. They don't have positive coefficients always. But there is a generalization of sure functions, which is the Schubert polynomial. So you guys probably know more about it than I do. These are indexed now by permutations. They are not necessarily symmetric, and they encode the cohomology of Lag varieties. I'm not going to define them fully here, but there is a special case when W is a vexillary permutation, so it means avoid certain patterns, 2, 1, 4, 3 pattern to be precise, then the Schubert polynomial is what's called the flagged sure function. So it's certain type of generalization of this thing here. And there are two identities in the literature about Schubert polynomials. One is McDonald's identity, that if you take a Schubert polynomial and you take, so this IDT means you take the identity permutation 1 and so on up to T, and then you have some other permutation W, which you basically shift and attach in the end. So you shift the entries by T and you attach basically the disordered parts of the permutation comes in the end. Then if you can evaluate this as 1 over the number of inversions of this permutation W, go over all reduced words, so ways to write the W in terms of as a product of adjacent transpositions. And for each adjacent transposition, you will record AI is the index at which it's happened. So basically, you're switching AI and AI plus 1. Then you have this factor, so T plus AI. And so, of course, these are all positive. So what you get here immediately is polynomial with positive coefficients. And the Flach-Schur functions, if you take this W to be vexillary, so this identity actually holds for all possible permutations, but if you take the W to be vexillary, you can evaluate the Flach-Schur function. Turns out it's the order polynomial corresponding to the poset to the straight shape associated to W. This comes from the Rothe diagram. There is a way to associate the Young diagram to our permutation. So I don't want to go into all these details and define all these notions, but the point is that by putting these two identities together, you already get for free, in some sense, that the order polynomial of a straight shape. So plane partition has positive coefficients. Then this is an identity also that was observed by Fomin and Kirillov about 30 years ago. So we have this beautiful formula. So there is a way to make it a little bit more explicit and say what these Ri's are, but I'm not going to write it here. But this only works for straight shapes. For skew shapes, there is no natural way to repeat this analysis at all. And so we did a lot of experiments trying to develop the Schubert calculus, so that didn't work. Okay, but it turns out there is something else we can do. So if we take a poset, doesn't matter what the poset is, and evaluate the order polynomial at x plus y. So you can think of x and y as positive integers. Then, so as a function of these two positive integers, how do you evaluate the order polynomial? Well, you break the posets into the elements which are going to be less than or equal to x. This is going to give you an ideal I. And then the other elements, the remaining elements of the poset, they are going to have values going from x plus 1 to x plus y. Or if you shift the numbers, then it is exactly the number of order preserving maps going from 1 to y. So this, for each division of elements into smaller group and a bigger group in the poset, you enumerate the number of order preserving maps for the first part, and then the second part, you multiply them together, you sum up. This gives you all possible ways of assigning the values in the poset from 1 to x plus y. So actually I didn't write it, but so if you teach binomial identities in the very special case of a chain, this is the true Vandermonde identity. Okay, so that's kind of a obvious combinatorial result. What you can do with it is, now you remember this is a polynomial and x and y are variables, and you can all set them to be equal to the same variable t. So now remember that this is a polynomial in t. It has some kind of coefficient. We don't know what these coefficients are, but they depend on just on the poset. So if we write our order polynomials, we expand them in terms of the coefficients. And we use this identity. Now, of course, I can be the empty set, and I can also be equal to P. So you need to remember that the poset here is going to appear twice. So what happens in the end is if you equate coefficients in front of t, you get this convolution on the right side. But on the other side, you have 2 to the k for each coefficient, 2 to the k minus 2, because you're repeating the poset twice. And so you can express the coefficient at t to the k in terms of as 1 over 2 to the k minus 2, and then this convolution of coefficients summing over all strict order, so non-empty and non-equal to p order ideal. So these are strictly smaller. Okay, so that works only if k is not 1. If k is 1, we don't get anything out of this identity. But what this gives you here is a certain basis for induction. And so we can formulate this as a meta theorem. So if your family of posets is such that these order ideals are also part of the family for each poset, so it's a poset closed under taking lower and upper order ideals. And we also have that the linear coefficients are non-negative because we cannot extract anything about linear coefficients from this identity. If you have the linear coefficients are non-negative, then basically you have all coefficients are non-negative. And actually, if you scale them by n factorial, they become integer, the coefficients of the order polynomial. So that's then n factorial times the order polynomial has non-negative integer coefficients. Okay, so basically what the theorem somehow says is what I was observing earlier, that the linear term somehow contains the complexity of the problem. And so as long as you get non-negative linear terms and you are in such a family of posets that contain each other, then you actually get that the order polynomial is also always positive. And in particular, if you have a skew shape, an order ideal of the skew shape is another skew shape, and the rest is also a skew shape. So the skew shapes themselves are closed under taking lower and upper ideal. So all it remains now is to figure out what the linear term is. And so here is the linear term. So if we have a skew shape lambda over mu, the linear term in the order polynomial can be explicitly calculated from this. And as long as the skew shape is connected, if the skew shape is not connected, then the linear term is actually 0. So how do we prove this? We do need to know something about the poset. And in this case, we have a formula for the number of plane partitions, skew plane partitions as a determinant, this Crever's formula, determinant of certain binomial coefficient. So unfortunately, that determinant on its own doesn't give you the order polynomial positivity. So determinants are quite complicated. You have a lot, if you compute them, you have a lot of subtraction involved. So it's very hard to keep track of positivity from here. But we can extract the linear term. So we make a few observations. So the matrix entries are these binomial coefficients, lambda I minus mu j plus t. T is our variable here, minus 1. Choose lambda I minus mu j minus I plus j. So if j is greater than or equal to I, first of all, we have, because of the connectedness, we have lambda I strictly bigger than mu I. And of course, mu I is a partition, so mu I is greater than or equal to mu j. So if you expand this binomial coefficient, it starts with t plus lambda I minus mu j minus 1, which is a non-negative number, and then it goes down to some t minus, well, this is also positive. So because it goes through consecutive terms, at some point there's going to be a t, factor of t here. So this is a polynomial divisible by t. And so when you write down the determinant, well, it goes over all permutations. You pick these entries. If you want to get a linear term out of this product, you cannot have more than one entry where wi is greater than or equal to I. Because otherwise you're going to get more than one linear term, so the degree, it will be divisible by t squared. Okay, so now we observe, well, this I and j, so j is actually wi, it comes from a permutation, and so you can't have that all wi less than I. Yeah. So at least one of these wi is greater than or equal to I. And one case where this happens is when I is equal to 1. Another case where it happens is when wi is equal to L. So you get these inequalities. And so that you don't get more than one such instance, you're forced to have for this entry that W of 1 is equal to L, basically, so that these two cases coincide. And then for the rest, you should have Wj less than J. And this forces you, because it's a permutation, to have Wj equal J minus 1. And so you have only one linear term, you extract it from, you have only one term that contributes a linear term, you extract it, you get this guy, and now you expand and you get the linear term from this expression here. Okay, so this is basically, then with the method theorem together, this gives us that the order polynomials of skew shapes are positive. You can do this so you can apply this for various special types of posets. So for example, the zigzag fence, which just looks like this. The Creveras formula gives you this determinant. It turns out it has no negative coefficients, which you can compute. And then, of course, your natural question is, so the leading terms are just the number of zigzag permutation, alternating permutation Euler numbers. So what are the other terms? So what kind of permutations are they counting? So this is a natural first question you can start asking. You can do cylindric partitions. So basically, you can imagine, so with the cylindric partitions, you imagine that you're drawing this picture on a cylinder, and this row is kind of drawn on top somewhere. So there is a d which is telling you what the offset is. So this partition is drawn on top somewhere. So by the way, and so then it should respect the inequalities, the gluing inequalities between this row and this row. So these are, so now is on a plane partitions, they're weakly increasing. So as a poset, the Hasse diagram would look like this. And again, there are some ways to compute this with determinants. This time it's a big sum of various determinants, and things become quite complicated. So first of all, these posets are, of course, closed undertaking as a family, are closed under lower and upper order ideals. So the question is, how do we compute the linear term here? And it's not so easy, so we didn't really do this, but we conjecture that this is also non-negative integer coefficient. And if we have a circular fence, we can actually do this. So this formula becomes a little bit more manageable, and we can extract the linear coefficient out of here. And the linear coefficient is, again, some kind of sort of like an inverse binomial coefficient. Okay, so this is what one can, so there are other classes of posets that one may consider. I'm not going to say much because there is some work in progress going on. I will just mention matroid polytopes since you guys like matroids. So I think I don't need to define what a matroid is for this audience. But basically there are these bases which are subsets, which are subsets of elements with satisfying various exchange conditions. So you can create a polytope off of this matroid, and it's basically if you identify the elements with the set from 1 up to n, then the bases are like you can think of them as indicators. So they are subsets of 1 up to n, and for each subset you can form a vector which is basically a vector of zeros and ones. You have a 1 if the corresponding index is part of the base or not. So then the polytope is just the convex hull of these vectors with coordinates 0 or 1, which are encoding the base sets. And in particular is also a subset of the unit cube. So we can ask the natural question when is an order polynomial or when is an order polytope, so associated to a poset, also a matroid base polytope? And it turns out that this only happens when basically the poset is a disjoint union of fences and single element posets. So in particular, what we get is that the matroid, if the matroid base polytope is also an order polytope, then it's going to have non-negative non-negative rational coefficients. And in particular, would be Ehrhart positive because of the shift at t+1. So what we figured out just recently is, so you can consider a little bit more general class of matroids, the lattice path matroids. So what it consists of is you take two lattice paths, inner and outer, so Q and P. In this case, they are actually, you can think of them as the borders of some Young diagram. So you essentially have a skew shape again in between these lattice paths. And now you consider all possible lattice paths between these points, these green dotted lines that go between the two, so that they are contained in this shape. This is basically so this forms the set of bases of this lattice path matroid. We can actually encode it in terms of partitions that are contained in this inner and outer partition, mu and lambda. So here in this example, how do you record the set? You record the set of recording at which points the up steps happen. So here in this path R, we have, so 1 is horizontal, 2 is vertical. So you record 2, 4 is vertical, 7 is vertical. So you have 2, 4, 7. Lambda and mu in these partitions. You can, of course, write down P and Q in that sets as well. And if you write them as sets like this, then it's basically the bases are just the sets that are, the entries are sandwiched between the Q's and the P's, basically. This inequality set is satisfied. And then we compute some Ehrhart polynomial. So this is not this example, this is different, but you can compute the Ehrhart polynomial, and it has non-negative coefficients. And this is something we can actually prove using the stuff that we proved earlier is that the Ehrhart polynomial of a lattice path matrix based polytope. Too many words. Has non-negative coefficients. And so I guess I'm out of time, so I will stop here.
Thanks, Greta.
So there were some other things on poset inequalities, but this is the last slide.
So did you say that the Ehrhart positivity for the matroid-based polytope for the lattice path matroids actually follows from the previous result?
So it does follow from the previous results. It is it's basically a way the way we do this is a way to decompose this the Ehrhart polynomial as a sum of certain shifted order polynomials for this for various fences and I guess more generally skew-plane partitions, but in our case it's just ribbons. And because so there is this play between the variable t and the variable t plus 1. So the Ehrhart polynomial is ordered polynomial at t plus 1. So this gives us a little bit of wiggle room somehow because there are gonna be some negative parts, but because of this t plus 1 shift, things will cancel. So so the solution is certain decomposition. So naturally, I don't want to say too much before we write it. Well, before we publish it.
But it's not that the matroid polytope is an ordered polytope, but it's something
No,
more
it's not an
complicated.
ordered
Yeah.
polytope. No.
Right.
No,
Cool.
but there is a way to decompose it into pieces that would be ordered polytope. So basically, think of it maybe I guess as some kind of a triangulation.
Oh, that's very interesting.
Yeah.
More questions? Hi, Franco. Go ahead.
Hi. Greta, thank you very much for the nice talk. I'm sorry I arrived a little bit late, I hope